All right, let's look at some volumes of revolution here and some areas on our review here. So here we have a graph that's enclosed by the graphs of the natural log of x plus 1 and x equals 3 and the x-axis. All right, so let's graph it. That's always going to be important. So it doesn't need to be an exact graph, but we need to have a good idea here. Okay, so x plus 1 is going to be the natural log of x curve, move to the left 1. So it's going to go through 0, 0. Normally natural log goes through 1, 0. It's going to go through 0, 0. It looks something like this. Okay. And the graph x equals 3, 1, 2, 3. Okay. And the x-axis. So our shaded area is right in between here. All right, so first of all, let's find the area of that. Well, the area here, it's just going to be the area underneath this curve. So this is going to be the integral from 0 to 3 of the natural log of x plus 1 dx. Using our calculator, that comes out to about 2.545. Okay. How about if we revolve this around the x-axis? Well, we're going to take that and we're going to revolve it around the x-axis here. So it's going to look like that. Okay, so there's our cross-section. So our radius is just the function here. So our radius is f of x. And so we're going to take a slice. So we think about the area. The area of that curve is going to be pi times the function squared, f of x, which is natural log of x plus 1. And that'll be squared. So now our volume is going to be the integral from 0 to 3 of that thing. So we're going to pull the pi out. We got the natural log of x plus 1 squared dx. And that comes out to about 8.158. By the way, when you get this in your calculator there, you can just bring this back and tweak it a little bit. You don't have to retype it completely every time. So if we want to find the volume of the solid when we rotate around the line y equals 3, okay? The line y equals 3, well, that's this line here. Whoops. So y equals 3 goes like this. Okay, so we're going to take this and we'll move it. I'll go ahead and redraw it here. So now when we take this or revolve it around there, it's going to be a washer. Okay, and so we got to think about the big radius. So the big radius is going from the line 3 down to the bottom. So the big radius is always 3. And the little radius from the center to the let's see, right about here. Let's give that a green line there. Okay, so this little green line right here. Okay, that's going to be, all right, well, what is going to be? It's going to be this value of 3 minus the function. So 3 minus the function. So 3 minus the function, which is natural log of x plus 1. Okay, now we know that area of a washer is pi times big R squared minus pi times little r squared. And then the volume is going to be the integral of that. So let's go ahead and integrate that. So we're going to have the integral of pi. We can pull those pi's out. And we got big R squared minus little r squared. All right, and that is dx. Let your calculator do the work here. And that should give us about 39.817. All right, now we're going to take that solid or that graph, and we're going to revolve it around x equals -1. All right, so around x equals -1. So let's get rid of this thing here. So x equals -1 is over here. Okay, so we're now going to need to change this function. Okay, and because we're going when we rotate this, we're going to be rotating around x equals -1, or revolving, I should say. And we're going to get this washer, something like that. All right, it's a little lopsided, but that's the idea. Okay, so we're now going to have this horizontal. Now we can do this in two ways. We can do this in the washer method, or we can do this in the shell. It's easier with the shell method, but I know that's kind of new to us. So let's do washer method first. And so what we need to do is we need to solve this and make it an equation of x in terms of y. So let's take y equals natural log of x plus 1. Okay, let's write this as e to the y equals x plus 1, subtract 1, and so x equals e to the y minus 1. Okay, well, that's our function of x. So now we can take this, when we revolve this here, this point right here is that x value. Okay, and so this distance I'm just coloring red there is going to be 3, because this has an x value of 3, minus the function. Okay, so that's, actually, I'm sorry. That's how long that line is. That's very true. But that's not what we want. We want to know this big radius. The big radius is going to be 4, right? Because this line is at 3, and this at -1, so it's at 4. So big radius is going to be 4. Okay, the inside radius right here is going to be the function minus this x value, which is -1. So the little radius is going to be our function e to the y minus 1 minus -1. Okay, and well, that's going to simplify out. So that -1 plus 1 is going to be e to the y. All right, that turns out pretty nice and easy. So the area is pi times big R squared minus pi times little r squared. And now we'll go ahead and find the volume by integrating that. Now we can pull the pi out, the common factor there. Times 4 squared minus e to the y squared. If we want, we can write that as e to the 2y dy. All right. So we'll see what the calculator has to say. Oh, we need to take that from 0 to 3. In fact, all of these here, I think I skipped that last one. That was 0 to 3. They're all 0 to 3. Okay, so let's see what the calculator has to say about that. I just entered in my calculator and I got like -400. That's a problem because the volume can't be negative. So what happened? Did you catch my mistake? Well, the mistake happened right here. Okay, we're not going from 0 to 3 anymore because that is an x value. What is the y value we're going from? Well, we're going from a 0 to whatever this is. Okay, well, what is this? This happens when x is 3. So when x is 3, what's the y value? Well, we can plug in 3 here, and we have y equals the natural log of 3 plus 1. This is a natural log of 4, which is not a whole number, so we'll leave it as a natural log of 4. Okay, now, that means for this y here, we need to go ahead and change that to not 3 here, but we need to change that to the natural log of 4. Okay? And now when we do that, we get 46.121. Right, that was a lot of work. So, this is where the washer method is not the best method. Okay? So when we're revolving around the y, okay, or a vertical axis, I should say, when we're revolving around a vertical axis like this, and we, instead of using the washer method, now if we use the disk method, that's not that bad. Disk is usually not that bad. But anyway, still, it gets complicated sometimes to change this into x as a function of y. So another method is this. So that was the washer method. Let's go ahead and try a different method here. And let's try the shell method. So here's how the shell method works. All right, now we didn't talk a lot about it, but let's see what happens. Okay, so the shell method goes like this. We're going to take a sample vertical line here. Let's get rid of this red line here if I can. There we go. We'll get rid of that. Okay, so get rid of all this extra stuff. Okay, so for the shell method, we're going to imagine a cylinder made from this. That red line is the height of this cylinder, and we're going to, as this spins around, it'll make this cylinder here. Okay, and imagine this is not a solid cylinder. This is just the lateral area. Okay, so this is a very thin lateral face of a cylinder. So we're not talking about the area on top or bottom. We're not finding the volume of the cylinder. Okay, and remember the area actually the lateral area, so we can use LA. So lateral area is the circumference times the height. Okay, well, the circumference is 2 pi r times the height. Okay, what does that mean? Well, we need an expression for the height. Well, what's the height here? Well, the height is just found by the function. Okay, now we don't need to change it. This height is a y value, which is a function of x. So it's just this function right here. Okay, so the height is ln of x plus 1. Okay, so let me come back down here. Okay, and I'm gonna do this problem separately. Here's the shell method. Again, we'll write down volume equals 2 pi r, which is the circumference, times, I'm sorry, not volume, but that's the lateral area. The lateral area is 2 pi r times the height. Okay, well, we just found out that the height is just that natural log of x plus 1. Okay, the height is determined by the function. Well, what is this radius? Okay, let's figure out the radius. So we're going to pick, here's the whole idea. We're going to pick an x value at some random spot in between 0 and 3. So when we pick an x value, the height is the natural log of x plus 1. What's the radius? Well, the radius is going to be this distance right here. What is this distance? It's 1, because 1 is the distance from -1 to 0. Okay. Minus x, or actually x minus -1, we might say. So this value is x, so our radius is x minus -1. In other words, x plus 1. So this distance from here to here is 1 plus this x value. Okay, so the radius is x plus 1. Again, we're choosing a random x value. So the radius is, we said x plus 1, so 2 pi times x plus 1. So there's an expression in terms of x for the lateral area of that shell. And there it is. Well, we're going to find the volume by finding all these shells. Okay, so, there's going to be another shell right here, so on and so forth. All right, so there'll be a whole bunch of shells, and all these shells together will make the figure that we get from revolving this volume. Okay, that's the shell method. And all we got to do, okay, so notice how it's a lot easier. We're almost done. So all we got to do here is integrate. So let's integrate, find the integral. Now, of 2 pi, which of course I could go outside, x plus 1 times the natural log of x plus 1. And that whole thing dx. By the way, remember when you put this in your calculator, you need this whole thing in parentheses. Actually, you probably wouldn't in this case because these are all being multiplied. And all the pluses need to be in parentheses. So anyways, now what's our bounds here? Well, the bounds are x values. So we're changing x values. So we're picking an x value, and that determines the shell. So the x value is going from 0 to 3. So we don't have to do any of that weird converting. The x values are just going from 0 to 3, and that's it. And if we go enter this in our calculator, hopefully we'll get 46.12. And there's a little screenshot for you. It does get the same thing. So here we went through all of that for the washer method. And there's our volume. Here it is with the shell method. There's our volume, okay? So you don't have to use the shell method on that. But anytime we're revolving around a vertical axis, shell method is really nice. Okay, moving along here, all right? So we have the region. S is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a semicircle. Find the volume of the solid, all right? So we've got that, so I'll sketch it here again. We've got this shape again here. That's at 3. There's our shaded region. So that's the base of our solid. We're going to go perpendicular to the x-axis, so we're going to take a sample length, okay? And so this is going to be, in this case, the diameter, be the side of a shape, or a diameter. It's going to be, we're going to put a semicircle on this, right? Okay, so a diameter here is just the ln of x plus 1. That is that function there. Okay, so that's our diameter. So the radius is 1/2 of that. So the area of a circle, actually a semicircle, is half of pi times the radius squared. And the radius is 1/2 ln x plus 1. Okay, so we have, again, area of a circle is pi r squared, so pi times the radius squared, and we have half of that. So this is the area of the semicircle. Okay. Semi means half of a circle. Okay, so all that's left here is to take the integral. So we're going to take the integral from 0 to 3 of this. Now let's go and clean this up a little bit. All right, this is 1/2 pi times 1/2 squared is 1/4 natural log of x plus 1. And whenever you simplify this, you should get this 1/8. All right. So, and if you want to memorize, you know, a shortcut, notice it's always going to be 1/8 times pi. Oops, I lost the squared, huh? Squared on this natural log. So it's going to be 1/8 times pi times the radius, or actually the diameter squared. See, that's the diameter. Okay, so if you want to memorize things, if you're big on memorizing things, the area of a semicircle, and it looks like it's going to turn out to be 1/8 times pi times the diameter squared. Okay, so there's a pretty little formula for you. All right, so we have 1/8 times pi, which we can go ahead and put that outside. Okay, 1/8 pi. This is our volume. And this is the natural log of x plus 1. And that whole thing squared. Okay. So, and that's dx. So see what our calculator has to say about that. And we end up with 1.020. Now it's actually I think it was 1.01979, something like that. But remember, when you cut this off here, and for AP standard, we're going to round to the nearest 3 decimal places. So this 19 goes up to a 20. So there you have the all the different methods of finding volume. Now we can have different shapes here, but there's different types. Okay, finding the area, finding volume, rotating around x-axis, rotating around a vertical line, or a horizontal line, that is, a vertical line, and a solid of known cross-section.